H and talking about gyrochronology. Go ahead.
All right. Hi, I'm Lucy Liu. I'm a postdoc at American Museum of Natural History. And today I want to advertise this first empirical gyrochronology relation that works for single field stars greater than 4 gigayears. So the effect I want from this talk is after you hear it, and next time you hear someone say, oh, I thought gyrochronology doesn't work for old ages, I want you to point them to me. So here's a brief outline for my talk. First, I'll briefly introduce gyrochronology and some empirical methods to calibrate gyrochronology. And I'm kind of going to scan through methods because of time, but I'm going to talk about how we can actually use kinematic ages to calibrate gyrochronology, and how, in the result, I'm going to talk about how we can use these kinematic ages and we discover an abrupt change in stellar spin down at the fully convective boundary, and how we calibrated this empirical gyrochronology relation. So in order to talk about gyrochronology, I have to put out this plot by Skumanich 1972, in which that he discovered that lithium, rotation velocity, and activity all decreases with age. So what gyrochronology is based on is the fact that rotation periods of a star decreases as square root of age. That's what we call a Skumanich spin-down law. And based on this principle, Sidney Barnes developed gyrochronology, in which that he mentioned that if you have a star, a field star with rotation period and color, you can use these gyrochronology isochrones to age date these stars. So what really revolutionized gyrochronology is Kepler, in which Kepler is able to provide tens of thousands of rotation periods of measurements. And I'm going to show these plots over and over again. On the x-axis, I'm going to be showing color or temperature, and the y-axis, I'll be showing rotation periods. And if you look at this rotation period distribution and you think it looks familiar, that's because it does look like Mr. Earthworm, thanks to Dax. And all these substructures kind of show us that things are not as simple as we thought. Because if stars do spin down Skumanich style, then we will not be seeing these gaps and pileups as we're seeing here. So as a result, gyrochronology relies very strongly on empirical calibration because we don't understand magnetic field that well in star yet. And there are a few different popular ways to calibrate gyrochronology. First is open clusters, which are showing in these confined sequences here. However, we don't have a lot of rotation measurements that are outside of the solar neighborhood. So it's very hard to get rotation measurements for open clusters older than 4 gigayears. So that can only be used for calibrate gyrochronology for younger stars. And we can also use astroseismic ages, which also has been done, but astroseismic signal decreases dramatically once you get to lower mass stars. So it can mostly be used to calibrate gyrochronology for solar type. And there's also wide binaries that we can use, but we don't have a very fully consistent sample across the entire rotation period and temperature space so far. So we run into a big problem that we don't have calibrators for these very low mass, especially low mass old M-dwarfs. And since last year, Gaia DR3 came out, it provided tens of millions of RVs for nearby stars. So it's a great time to actually calibrate gyrochronology with kinematic ages. And not only can it be used to calibrate low mass stars, we can get a consistent sample across the entire rotation period and temperature space. So in particular, what we're using is the age velocity dispersion relation, in that the velocity dispersion increases with age. So here's a proof of concept taken from Angus 2020. On the x-axis is showing rotation period, which is a proxy for age because stars spin down over time. On the y-axis is showing Kepler VB measurements, which is a proxy for V vertical velocity. So as you can see that as you increase in rotation period, which is increasing in age, you see this increase in velocity dispersion. So that's what we expect. So we can use kinematic ages to calibrate gyrochronology. And if you discover this, that's true, that there is some very fast rotating stars that have a high velocity dispersion than what it should have, and thus most likely binary stars because they're in binary interaction, so it spins up the star in a way. So as a result, kinematic ages cannot be used to calibrate gyrochronology for fast rotating stars. So that's one of the caveats. So to calibrate gyrochronology, we started with 20,000 Kepler rotators with Gaia DR3 kinematic information showing here. And as you can see, we're actually missing a lot of low mass stars, which are the prime target for gyrochronology because they spin down faster as they age. So I'm not going to go into the detail, but basically we fixed that with using DTF, and we're able to double the kinematic sample that we have. So in total, we have 60,000 kinematic stars with kinematic from Gaia DR3 from both Kepler and ZTF. I'm also not going to go into detail how we calculate kinematic ages, but here is what it looks like if you color them by the ages that we calculated. So we have something that we expect. Stars gradually spin down over time, so the youngest stars are faster rotating and the older stars are slower rotating. And as expected, we don't do so well for the fast rotators because they're most likely binaries and some other systematic. And one thing, if you squint and look at this plot long enough, you might discover something weird is going on here, which is around when stars transition from partially convective to fully convective. So what we can do is we zoomed in and looked at these plots. And then if we just look at stars in a narrow temperature band around 3,400 to 3,500, you see that at first is what we expected, that stars gradually spin down over time. So you go from young to old as they spin down. However, we have this very weird group of young ages that are rotating very slow. And so we were thinking, okay, this is near the fully convective boundary. So it must be due to that there are two different populations of stars. So that is what we do is we looked at stars in this temperature band and we plotted their kinematic ages versus period, and we separated stars that are fully convective and partially convective based on the joule gap. So you can see that these fully convective stars, which are showing red, spin down faster compared to these partially convective stars. And also don't have too much time to go into detail, but I also want to point out there's a talk coming out tomorrow by Federica at the Magnetic Field in Sun and Low Mass Stars plenary session, which she will be talking about some white dwarf, M dwarf binaries that also show similar things, and also a poster by Lydia and also Victor seeing similar things around the same time. So let's go back to the kinematic ages. And what we did is we calibrated a gyrochronology relation using these kinematic ages for the partially convective stars and fully convective stars separately because they spin down differently. So this is what it looks like. These are different gyrochronology isochrones. And we calibrated not only using kinematic ages and also the cluster ages as well. And if you want to use this package, it's on my GitHub. And all you need to input is a temperature and a period. And from that, we're able to get around 100,000 dwarf ages from this calibrated gyrochronology relation. And for the next few minutes, I'm just going to show some diagnosis plots to hopefully convince you that these are real ages that we're getting. So on the left, I'm showing these predictions from our model for open clusters compared to the different open clusters. And of course, we do well because we did use open clusters in our training set. But on the right is showing x-axis the astroseismic ages that we have, and the y-axis the prediction from our gyrochronology model. And these stars are actually not in our training set at all, so we're just predicting them as test set. And these stars are colored by metallicity, and you can see that we're able to mostly predict or infer the same age for astroseismic ages, all the way up to 10 gigayear. And we have a scatter around 1.5 gigayear for that. And another test we did is a self-consistency test in which that we find stars which the primary star and the secondary star are both in Y binary. So they're Y binary pairs. And on the left, I'm plotting the primary gyrochronology age predict from our model. And the y-axis is predict the gyrochronology age for the secondary. And they're colored by the difference in temperature. So as you can see that we have a pretty self-consistent model within around 1 gigayear of uncertainty across all temperature ranges. So on the right, I'm plotting around the same thing, but colored. So this is temperature versus rotation period. And these are the Y binaries we have, but we color by the difference in their predicted ages. So from the primary and the secondary. And you can see a few things that we don't do well, which is as expected. First of all, is the fully convective limit, which is hard to separate fully convective and partially convective stars first. And also there might be other things going on right when the transition happened. And also there's these, we don't do too well at the intermediate period gap, which is also expected. And these stars that might be going through weakened magnetic braking. So I just also want to advertise that we have around 300 unique exoplanet host stars that can be used to understand planet evolution. So if anyone's interested, either download the package or talk to me. So here are some takeaway points. First, that kinematic ages can be used to calibrate gyrochronology beyond 4 gigayears. And then we discover an abrupt change in stellar spin down using the kinematic ages. In the end, we now have 100,000 gyrochronology ages for dwarf stars in the extended solar neighborhood, in which 300 of them are unique exoplanet hosts. So that will open up a lot of opportunities to study extensively what's going on in the solar neighborhood. Thank you.
Great questions. Here.
Thank you very much for the I'm Yuta from University of Colorado. I have a question about the rock changes fully convective power. Do you have any information on activity changes?
Yeah, so the question is, does the abrupt change at the fully convective boundary coincide with any activity changes or other things? I think the general understanding is maybe no, but it's hard to say because the activities are calibrated with the convective turnover time, which is also something that's model dependent. But tomorrow, Seth is going to give a talk on actually if you, I'm not going to spoil it, but you can calibrate Rossby number using empirical method. And it seems like maybe the activity relation does hold through partially and fully convective stars.
Online question here.
Thank you. Did you already have some look at magnetic properties as a function of cumulative ages?
Yeah, so basically the spin down law. Okay, so the question is if I have looked into how stars spin down, I guess magnetic, like momentum loss with kinematic ages, sorry, and magnetic properties and how it changes with age. And I have not. So I looked into a little bit, but that will be a future project. And since we have all these ages, it will be very interesting to look into that. Yeah.
Right, one last one here. Way back there. Who's gonna get there first?
Hello, I'm Jonathan Gagné from the Montreal Planetarium. Excellent talk, thank you. I was curious, what is the minimum age at which you would trust GP channel, given that you calibrated it using
Yes, that's a great question. So the question is, to what age do we trust this gyrochronology relation? So I would say around 1.5 is when we can start trusting it. And it is calibrated to 0.6, but I would say 1.5 is like the better cutoff to use. Yeah.
All right, thank you very much.